Hello again, grade 9. So we are going to cover Ohm's law and the resistance formula. This is on page 16 of your books. Okay, so please make sure that you're on page 16. And this should not take that long at all. This should be super duper easy for you. And what's going to actually happen is you guys are going to complete page 17 and 18 by yourselves. So make sure that you open your book to page 16 and let us continue with the video. Okay, so the slide is a bit scary, but I need you to just chill. What did we do before? What did we do in the last lesson? The last lesson we covered the gradient or the slope of a directly proportional graph. And in that directly proportional graph, we looked at your voltage or your current over your voltage sort of thing. So in this situation, what we saw was that as your voltage increased, so did the current. So what you should have actually done is put voltage on the x-axis and current on the y-axis. So in the image that we gave you, those two were reversed, but they work together, so it's fine. It's not the end of the world. The point I'm trying to make here is that the slope or the gradient was that resistance because it remained constant. We didn't change anything. Okay, so that the results of that experiment explains Ohm's law. And even though he's an old German physicist and he looks very stern and not very happy, grade 9s, this guy knew what he was talking about. So the current through a conductor, remember conducting wire, is directly proportional to the potential difference across the conductor at a constant temperature. If the temperature remains the same, as soon as the temperature changes, that proportionality is going to be different. So what I want you to do is I want you to go to page 16 and I want you to just fill that box in, because everything we did in the previous section actually just, all it was Ohm's law. That's all we were showing you. At the top of the slide, it shows there that current tends to move through conductors with the same degree of friction or opposition to motion. So that sentence basically means it moves through conductors with the same amount of resistance. This opposition to motion is more properly called resistance. Now remember, this is not in your books, but you can add this in. You can write this on a piece of paper, you can write it on the side, the back of your book, whatever's going to help you. You know how you study. So write it in if you want to. It's not compulsory, but it could help you. The amount of current in a circuit depends on the amount of voltage and the amount of resistance in the circuit to oppose the current flow. Just like voltage, resistance is a quantity relative between 2 points. What does that mean? Okay, what is potential difference? It is the amount of energy between 2 points, okay, of potential energy between 2 points. Resistance can be the same. It is like in the light bulb. It would be, what is the resistance of the light bulb between 0.1 and 0.2? For this reason, the quantities of voltage and resistance are often stated as being between or across 2 points in the circuit. So I will say the resistance across the battery, the resistance across the light bulb. Then you understand the resistance of that light bulb or the resistance of those light bulbs. Does that make sense? So guys, just have a read through this. Make sure you understand exactly what's going on. And the next slide, we are going to go through some of the formulas that you guys need to be comfortable. You need to know those formulas. However, in tests and exams, we do give you the formulas. I'm sure Mr. Ginsberg has told you that already. Okay. So right underneath your Ohm's law definition, you will see there's a little box there. And that little box is going to be your section or space where you're going to fill in your relationship between resistance, current, and potential difference. And the maths of this are as follows. If I want to work out voltage, I'm going to multiply current and resistance. If I want to work out current, I'm going to divide voltage and resistance. If I want to work out resistance, I'm going to divide voltage and current. So please write in all three, because they show you how you can manipulate the formula or the triangle. Draw in the triangle as well, grade 9s. And then on the right-hand side, you need to write in these physical quantities and make sure you include the correct unit. So for resistance, we are measuring resistance in ohms. We are measuring currents in amperes, and we are measuring voltage in volts. Okay, so make sure you cover that. The next slide I'm going to show you is going to be more formulas, but these are specifically designed for either resistance in parallel and resistance in series. Okay. So these are our resistance formulas. So before you do anything else, I want you to look at total resistance. Total resistance is the sum of resistance in series and resistance in parallel. We work out resistance in series by just adding the resistance of each resistor. So if I've got 2 light bulbs and each light bulb is 2 ohms in series, I'm going to go 2 plus 2. Therefore, my resistance in series is going to be 4 ohms. It's a bit different if I am going to be calculating resistance in parallel. Now remember, current splits in parallel. Therefore, the resistance is also not going to be as hectic in parallel as what it would be in series. In actual fact, more resistors in parallel decrease the resistance. So we are looking at some sort of division. We are looking at splitting it. So if I had 2 resistors in parallel and each were 2 ohms, I would say 1 over RP. Therefore, what am I doing, guys? I am dividing. This is division. So 1 over RP is going to be 1 over 2 plus 1 over 2. And then you are going to flip that fraction, and you are going to work out the ohms in a parallel circuit. Please don't worry about this. We will go through this properly. Even though I'm going to give you the exercises to do and you're going to try and do them, I will give you the answers. I don't want you to worry. This type of thing takes practice. It doesn't just happen overnight. So like I said before, series network, it tends to be a lot easier. All we do is add up the resistors. It's a sum of thereof. And then in the parallel, the equivalent circuit resistance is calculated differently. So it is the reciprocal 1 over R value of the individual resistances all added up. Okay. So resistance in parallel is different to 1 over RP. And you'll see this when we do little exercises. So make sure that you fill this in. And then if I had a combination circuit, so a combination circuit is that of series and parallel, I would take those two values and I would add them together. And that would be my total resistance. The next slide I'm going to show you is an example of putting these formulas in practice, and then you guys are going to actually do page 17 and 18 by yourselves. All right. Okay, so before we look at the bottom of page 16, I just wanted to show you this again to make you see, and maybe you should write this in to help you. So I want you to look at the top of the slide. That is an example of a series circuit resistors. So each little box represents a resistor. Remember what I said to you guys in class, you are not going to use a resistor with a squiggly line. You are going to use a resistor with a box because that is going to be more accurate. Okay, don't draw the one with the squiggly line. If I'm working it out in series, all I'm doing is R1 plus R2 plus R3. So in this situation, the total resistance is going to be 100 plus 82 plus 1. Therefore, my resistance for my series circuit here is going to be 183 ohms. Now, it's a little bit different if you're looking at parallel. I want you to look at the bottom of the slide. You can see we have 3 resistors in parallel. Now, these could be light bulbs or resistors. Please bear that in mind. I have resistor 1 is 10 ohms, resistor 2 is another 10 ohms, and resistor 3 is 33 ohms. Now, if I'm working this out, I'm going to go 1 over RP is equal to 1 over 10 plus 1 over 10 plus 1 over 33. And if I work that out, it should give me a total of 0.23, 1 over 0.23. Once I flip this and I work this out, it should give me a total of 4.35 ohms. Okay, so make sure that you follow the formula. If you guys are getting stuck, please drop me a message. So this is the bottom of page 16. The first figure, the first image shows resistor 1 and resistor 2. And the first resistor is 2 ohms, the second resistor is 5 ohms. Very simple resistance series. It's going to be 2 plus 5. My resistance is going to be 7 ohms. So please write that in. Then for my parallel, it's exactly the same resistance for each resistor, except now they've been connected in parallel. Okay, so here my resistance in parallel is going to be 1 over RP is equal to 1 over resistor 1 plus 1 over resistor 2. What is the substitution of that, grade 9s? It's going to be 1 over 2 plus 1 over 5. Therefore, I am going to have 1 over RP that is equal to 7 over 10. 7 over 10. And I'm going to flip that value and I'm going to divide it. That should give me a resistance of 0.7 ohms. The 2 steps in the middle there are not necessarily, so these 2 steps here, okay, are not, trying to draw that in, are not necessarily absolutely vital. You don't have to draw them in, but sometimes it helps. Like with the previous example, you could have just flipped it in the previous, flipped 1 over 2 and 1 over 5, and you would have come to 0.7 ohms. Make sure you flip it in the end. It's very important. Okay, so I think that is it for today. Zoe, come say goodbye, baby girl. Come. There we go. Zoe's little camera show, but she says goodbye, grade 9s. And I want you to please try and complete the exercises on page 17 and 18. And then on Wednesday, we're going to carry on with factors of resistance. Okay, have a great day, grade 9s. Cheers.